Okay, we're going to do another worked example on proton NMR, and before we start with a real example, a real exam question, what I'm going to do is go through the steps. There's about 5 or 6 steps involved in reading the exam question and getting to construct a whole molecule from the NMR. Okay, so first step, I'm going to actually call it step 0 because it's unorthodox. It's not in the mark scheme, so you won't get a mark for doing this step, but I think it helps. And I'm going to call this step check for double bonds. Okay, check for double bonds. Now, when I learnt about NMR, then I learnt something called hydrogen deficiency index, which is not in your spec. So we're not going to do hydrogen deficiency index, but what we are going to do is what I did in the worked example number 1. So I just had a look at the general formula for an alkane. If you remember, that's CnH2n plus 2. Because if it just does happen to work out that the number of hydrogens is twice plus 2 the number of carbons, then it tells you that there's no double bonds. And pretty much all of these examples are going to have oxygens in them. And so what that can tell you is what type of molecule you're dealing with. You know, for example, if there's no double bonds, then it's quite likely to be an alcohol or an ether. And if there is double bonds, it's quite likely to be an aldehyde or an acid. So although I'm not going to teach you about the whole of hydrogen deficiency index, because you've done this before at GCSE, I think this is valuable. Okay, so we call that step check for double bonds, and we're going to call it step 0 because, like I've said, there's no marks in the mark scheme for it, but it is useful and it stops you making a mistake when you look at your infrared spectra. Okay, so let's call the first official step step number 1, which is check the infrared spectrum. So when you do this little analysis here, you're going to have an idea about whether it's an alcohol, an ether, a carboxylic acid, an aldehyde, etc. You're going to have an idea already. So that means when you come to look at the infrared spectrum, you've got some clues already to start with, so that will help. So from the infrared spectrum, you're going to work out what sort of bonds are in there, so you're going to know whether it's which one of those 4 molecules or a mixture of those molecules. So there we are, simple step number 1. Step number 2, let's say we're going to count the peaks of the NMR spectrum. So we're going to count the peaks, and as you know, that it's going to tell you the number of environments that your protons are in. Okay, so step number 3, let's call it count or check the integral values. And they might be given to you in whole numbers already, or they might not, in which case, as we did before, you divide by the smallest number. And even then, you might not get whole numbers, you might get 1.5s, in which case, just like in empirical formulae, you're going to double it up until you get all whole numbers, because you can't have a part of a proton. And when you get all whole numbers, then you're going to count them and compare to the number of hydrogens in the molecule. All right, so you're probably given a formula of the molecule to work out its structure. All right, so you'll be given the number of hydrogens in the molecule. All right, and so then you want to count the number of hydrogens you've worked out from your integral values to make sure they're the same. So I'll just complete that sentence by saying in molecule that's in the question. Okay, so step number 4, you're going to investigate each peak. So peak by peak, you're going to go through it, and firstly, you're going to have a look at the splitting pattern, or you don't have to do it in this order, but you have to do all these activities. So you're going to have a look at the splitting pattern, and that's going to tell you about the neighbouring protons. And then you're also going to have a look at the chemical shift for that peak. Why don't I just write that? You're going to have a look at the chemical shift for that peak, and that's going to tell you. Now, I like that to tell me about how far the alkyl group is from an electronegative atom like oxygen or chlorine. Okay, so I'm going to put that in, how far it is away from. It saved me writing the word electronegative. Let me just write an oxygen or a chlorine. But in your alternative, and I think in these exam questions, it looks like you're more expected to use table B in the data sheet. So, if the chemical shift is 1.1, you look at 1.1 up in the data sheet and see what sort of proton that is. Okay, so we'll write that down as well, versus table B of the data sheet to check what type of proton it is. And once you've done that, you're going to construct a whole molecule. Alright, so last step, construct a whole molecule. And from the different bits that you've made up following this process, I just want to go back to integral values for a second, because once you've got the integral values, and that gives you the number of protons in that environment, then you can work out the groups those protons in. So if you've got a peak with 2 protons, or an environment rather, let's say with 2 protons in it, then it's going to be in a CH2 group. And if you've got an environment with 3 protons in it, it's going to be a methane group. So you can construct bits of the molecule from the integral values like that. So there we have it. We've got 5 steps. What we're going to do now is look at an actual exam question and follow that process and get to the structure of the whole molecule. So here I have table A and table B all on the same sheet, as well as the question paper. So it's a little bit busy, but let's see what we can do. Okay, so just going through the steps. We're going to start with this step 0, and as you know, we've got CnH to N plus 2 for a straight chain alkane. So we've got N equals 6, and 2N plus 2 is 12 plus 2 is 14. Okay, so conveniently, that tells us that R has got no double bonds. That's all it tells us. But then looking a little bit closer, we've got 2 oxygens in there. So if we've got a molecule with 2 oxygens but no double bonds, it could be an alcohol. All right, so you could have 2 hydroxyl groups and make it a diol. It could be an ether, and you could in fact have 2 ether links in it, or it could have 1 of each. We don't know yet, but what you can say from this quick analysis is that it's not going to be a carboxylic acid, because we haven't got a carbon double bond oxygen, and it's not going to be an aldehyde for the same reason. So that's what we think so far. You've got no marks yet, right? But we've got an idea that it might be a diol, a diether, or a molecule with, or an alcohol rather, with also with an ether link in it. Okay, so let's now look at the infrared spectrum, and straight away you'll see this familiar peak, which is broad and corresponds to this wave number here. All right, so straight away we can see that that's going to be an OH group there. So we know that it's either a diol or an alcohol with 1 hydroxyl and 1 ether link. Okay, so let's have a look. If it's going to be an ether, we're going to need one of these. So 1000 to 1300, right? So yeah, we've got a peak there. So it looks like we've got an ether link in there as well. So that would suggest so far we've got one hydroxyl group and one ether link in our molecule. To be doubly sure, let's check our carbon double bond oxygen. So that's just less than 1700 to just over 1700. Here's 1700. Okay, and we've got no peak there, so that says we haven't got one of those, which confirms what we thought earlier. Okay, so that's what we've got so far. We think this molecule R has got one OH group in it and one ether link in it. And while we're at it, of course, we've read this part of the question, and so we know that this is either a primary or a secondary alcohol, but not a tertiary alcohol from that little statement there. So now we're going to move on to our NMR spectrum, our proton NMR spectrum, and we haven't got the actual spectrum, we've just got this summary table of it, which is kind of them, unfortunately, because you know, you can get good at reading those, and that'll set you apart from the other students. However, here we can only answer the questions we've got. So let's have a look at this. First of all, let's talk about chemical shift. Here we've got a chemical shift of 3.8, which means there's less shielding at this end. Less shielding, so protons are a bit barer at that end, and our protons at the other end, at the 1.1 end, are, let's say, lots of shielding. Okay, and we've got oxygens in our molecule R, so what that means is that where there's less shielding, they're going to be near to the oxygen, or both of the oxygens. And at the other end, where there's lots of shielding, they're going to be far from an oxygen. And for more detail on shielding, see me in class. Okay, so that's that first part of our NMR spectrum. Let's now have a look at the integration ratio. So kind numbers already, no sort of fractions or anything that we need to ratio up. Let's just count them all. We've got 2 plus 3 is 5, plus 1 is 6, plus 2 is 8, plus 6 is 14. So that's the same number as our hydrogens in our molecule. So that's very convenient. So what we can do straight away is go through them one by one and say that this is going to be a CH2 group. This is going to be a CH3 group. Now, single protons or integral ones with singlets are in an OH group, alcohol group. And this is going to be another CH2 group, and this is going to be 2 CH3 groups, right, that are in the same environment because they're to do with the same peak. Okay, so that's what we've got from our integration ratio. And let's do our number of neighbouring protons. So let's say hash NP. So we're going to put this down here. So a triplet, of course, means that we've got 2 neighbouring protons. A singlet means 0, singlet means 0, triplet means 2, singlet means 0. Okay, so now we've sort of had a look at all our data. Let's see what we can deduce from that data. And let's start with our OH group. Okay, so we've got an OH group there for our integral 1 at 3.1 chemical shift. So we know that, and that's going to be connected to an R group, but we're just going to start with a carbon. So that's the first thing we can write down. Second thing we can write down is we can have a look at this CH2 group there. This CH2 group has a high chemical shift, all right, which means it's close to an oxygen. And this CH2 group has a low chemical shift, which means it's further away from a and oxygen. All right, so that suggests to me straight away that these two CH2 groups are connected to our alcohol oxygen here. Let's just, before we actually write those down, let's just check our sigma values, our chemical shift values. So we've got 3.8, right? So we could have a look at this one. Is that consistent? Yes, is the answer. And is our 3.1 consistent? Sorry, our 1.4 consistent. So 1.4 can't be this one, can't be this one, has to be this one. Alright, so that's just a CH2 connected to another carbon. Alright, so that is consistent. So now we can say that we have these two CH2 groups connected to the oxygen. Alright, so we've dealt with this CH2 group. Let's give it a tick there. And we've dealt with this CH2 group, and we've dealt with that OH there. Okay, moving on. Let's do our two CH3 groups here. Let's do these two CH3 groups. Now, they're two CH3 groups, and we know that they're connected to a carbon that has no hydrogens attached to it from this bit of information here. So that means that part of the molecule, all right, must be like this. That's our one CH3 group. That's another CH3 group, and they're attached to a carbon, of course, right? Where this atom here and this atom here are not hydrogen. They're not hydrogens. Okay, so that's what we know from integral 6 at chemical shift 1.1. We can't attach it to the rest of our molecule yet. So what we're going to do is we're going to have a look at the remaining part of the molecule that we haven't dealt with yet, which is this integral 3 at 3.2 chemical shift. Right, so it's a CH3 group with a high chemical shift. A CH3 group with a high chemical shift. So the high chemical shift means that it's close to an oxygen. And just checking out the table on the right hand side, it could be from this bit of data here as well. So if we're going to draw a CH3 group that's close to an oxygen, right, don't we just draw it like that? Okay, now we know it's an ether link, so this has got to be connected to a carbon. Alright, but I'm just going to cross that out so far because it's likely to be one of the carbons that we've drawn already. Okay, so now we've looked at all the bits of data in our NMR spectrum, the table of our NMR spectrum, and the last thing that remains to do is to fit these three parts of the molecule together. And it's difficult to explain in words, but going back to the two CH3 groups with a singlet of 0, so attached to no neighbouring protons, I think you can see from that bit of data and this bit of data that this group here has to fit onto that group there. Right? If we fitted our ether link straight onto the main group, you wouldn't be able to fit the rest of the molecule on, because that would be it. It would be two ends all closed off. Okay, so this group that I've circled has to fit on to the main part of our molecule, and then our oxygen needs to fit onto the remaining space on this carbon here. Okay, so I just changed colour, I don't know why, but let's do it. So I'm going to draw this ringed section of the molecule. I'm going to connect it up. Like that, and then that bond there becomes this bond here, and we're going to connect this one up here like that. So done, we think. Right, but before we move on to another question, we should check whether it makes sense. Okay, so how are we going to do that? Well, first of all, we're going to count our atoms, starting with hydrogen, to make sure that they add up to the 14 they're supposed to add up to. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So hydrogens are good. We can see 2 oxygens there, so that's good. And how many carbons we put in there? 1, 2, 3, 4, 5, 6 carbons. So it all balances. We could go through the environments. Okay, so if I've got another colour, let's do grey. Okay, we've got hydrogen in an environment there. We've got a pair of hydrogens in an environment there close to an oxygen. We've got another pair of hydrogens on a CH2 a bit further away from an oxygen. We've got 6 hydrogens here that are connected to a carbon that has no protons attached to it. And we've got 3 hydrogens here on a methyl group that is connected to an oxygen. Alright, so, and that's 1, 2, 3, 4, 5 grey groups. So it all seems to make sense. Alright, so I would personally leave that like it is and move on. The last thing to be said though in the video is that I've not written down all the steps that you went through. I've spoken them, right? So obviously if you're in an exam you have to write these steps down, like the steps we did on the earlier slide, to get the marks, because that's what you have to do. That's what the examiner's looking for. He has to give you a mark for something, so you have to write it down. And I would just reiterate the last point, that if you can't fit the difficult thing about NMR, proton NMR, is fitting the molecule together at the end. All right, and that's what freaks people out. But most of the marks are for the preliminary steps. There's only 1 mark for fitting the molecule together correctly. All right, and so 8 out of 9 are just going through the standard steps, which I think are less difficult and all of you can do. So good luck.